This is a film about thermionic valves, and more particularly about how they are made. You're no doubt familiar with this, an essential component of your radio or television receiver. And with this, its conventional representation in a circuit diagram. This particular valve is a pentode, and you will recognize its various parts: the envelope, the heater, the cathode, the control grid, the screen grid, the suppressor grid, and the anode. Now let's look at the actual parts and see how they're assembled into a complete valve. This is one form of cathode. It is a flat nickel tube, coated on the outside with an emissive material, a mixture of the oxides of barium and strontium. Here is the heater, spiralized tungsten wire, only 70 microns, or a little over 1/500th of an inch in diameter. It is bent into a V shape and is coated with an insulating layer of alumina. These are typical grids, flattened spirals of fine molybdenum wire, wound on two stout backbone wires. In the pentode type of valve, there are three grids: the control grid, the screen grid, and the suppressor grid. The anode in this particular valve is stamped out of sheet metal in one piece. It is blackened on the outside to help dissipate the heat developed in the anode by bombardment by swiftly moving electrons. These are mica discs carrying metal screens, and the electrodes you've seen are assembled concentrically between two of these discs. For purposes of demonstration, the operator's movements have been slowed down, and jigs are not being fully used. First, the cathode is fitted in the bottom mica. Then the control grid. The screen grid is next. Now the suppressor grid is put in place. The anode is added. And the top mica goes into position. After fitting one or two more small components, the valve assembly is ready to be mounted on its base. The base is a glass disc holding 9 connecting pins to plug the valve into the set, and 9 corresponding wires to which the various electrodes are connected. The glass base is made up from these components: a short length of glass tubing and these connecting wires. The connecting wires are made in 3 parts. First, the valve pin. Secondly, the connecting wire. And between them, a short length of metal, which has the same overall coefficient of expansion as the glass, and which therefore makes a good airtight seal where the wires pass through the glass. Now look at the finished base again. You will see that the wires are cut and bent to the exact positions to receive the lower end of the various electrodes. Now assembly and base are fitted in a jig, where they are held in the correct position so that they can be joined by spot welding. When all the connections have been welded, the assembly is taken out of the jig and a few further components added. The heater is threaded through the cathode tube and its ends welded to appropriate wires in the base. This small plate helps in dissipating heat by radiation, so keeping the control grid cool and reducing the risk of grid emission. It will be welded on the control grid backbone wires just here. This gauze cylinder acts as an electrostatic screen. This additional mica disc keeps the assembly central in the bulb. The getter, which contains a small quantity of chemical material that is evaporated after the valve has been pumped, combining with the small remaining traces of gas, so perfecting the vacuum. The getter plate which carries the getter. It is mounted at the top of the assembly and serves not only to support the getter, but also to prevent the getter material condensing on the valve electrodes. Here is the getter welded onto the getter plate. The bulb is a glass tube with one end closed, and to this is attached a filler tube in such a way that a passage is opened between the bulb and the tube. Let's push a wire through to show you. It's through the thinner tube that the air is withdrawn from the valve during the pumping operation. Now the electrode assembly is placed in the bulb, so. The junction between the base and the bulb is then heated, so that the two glass surfaces fuse together. The valve is then plugged into the pumping machine. The air is removed and the valve sealed off, leaving a short pip at the top, which is the remains of the pumping tube. The dark area on the inside of the bulb is due to the firing of the getter. Now let's go to the factory to see the valves actually being made. Of course, it isn't merely a matter of making just one valve having the required characteristics. Huge quantities must be produced, and each valve must give exactly the same performance. To control quality right from the beginning, production starts with chemicals, mineral salts, metals, and other raw materials, often in their most elementary forms. Here are the raw materials of glass: sand, red lead, soda, and a proportion of broken glass, technically known as cullet, which are melted together in the glass furnace. Many of the glass parts used in valve manufacture are made from glass tubing. From the tube-making machine, a column of molten glass is drawn upwards, an internal blast of air keeping the glass in tubular form and controlling its diameter. As it ascends, external air streams cool it and control the thickness of the wall. Here, the now solid tube is cut to standard lengths, and each length is gauged and weighed to check its dimensions. Bulbs for receiving valves are made from short lengths of glass tube. The tube is cut to length on one machine and closed at one end on another. Now the smaller tube is fused to the closed end. It is through this smaller tube that the air is removed from the bulb in the final stages of manufacture. After each stage in which glass has been worked, it is annealed by raising it above a certain temperature and then cooling it gradually, thus normalizing any strains set up in the material. Each bulb is inspected, and any which show defects are ejected. In this test equipment, a high-tension discharge is produced between two electrodes. When a good bulb is placed over the probe, the spark is extinguished. But if there is the slightest crack or flaw, the discharge sparks through, the faulty bulb then being rejected. Besides bulbs, all kinds of small glass sections are made. Here are a few examples. At every stage the components are checked. Here the thickness of the glass is measured with a micrometer. In other parts of the factory, other components are being made. So let's take a look at these now. We shall be meeting the glass again at a later stage. The heater is made from tungsten, and tungsten is the metal obtained from scheelite. The scheelite is weighed and tipped into a ball mill. Here it is ground continuously for 7 days to reduce it to a fine powder, which then undergoes various chemical treatments which yield pure tungsten in powder form. The tungsten powder is weighed out into suitable charges. It is placed in a steel mold, carefully leveled, and packed down. The mold goes into a hydraulic press, and a pressure of about 100 tons is applied. When withdrawn from the mold, the metal is in bar shape, but as yet it is very fragile. So the bar is now sintered. It is heated to a very high temperature by enclosing it in an atmosphere of hydrogen and passing an electric current of between 2,000 and 3,000 amperes through the metal. A temperature of 2,700 degrees centigrade is obtained. The tungsten now has a crystalline structure. The first process in wire making is swaging, that is, hammering the bar so that it becomes thinner and longer. In these machines, metal is heated and beaten with hammers in rapid succession, making it thinner, longer, and rounder. It is now ready to be drawn to still smaller diameters. Lubricated with graphite, the wire is heated and pulled through tungsten carbide dies by a chain-driven mechanism. This sequence, lubrication, heating and drawing, is repeated with smaller and smaller dies until the diameter of the wire has been reduced to about 1/50th of an inch. From this stage, diamond dies are used, until after some 200 or 300 drawings, the original bar has been transformed into as much as 200 miles of fine wire, of diameters down to 6 microns, or 3/10,000ths of an inch. Such very fine wire cannot be measured by normal instruments. Its diameter is therefore checked by weighing a known length of wire. It is also examined for roundness under a microscope. Molybdenum wire is also required in valve manufacture. For example, it is used for valve grids and filament mandrels. The molybdenum wire is produced from its ore in a very similar way to tungsten. Coiled tungsten wire for valve heaters is produced by winding the tungsten wire on a mandrel of molybdenum wire and later dissolving the molybdenum with acid. Now for some other valve components. Mica discs are stamped out of sheet mica and are checked for size and position of holes by projecting their image 30 times full size onto an illuminated screen, where the dimensions can be measured to within 1/500th of an inch. After this, the discs are examined and any broken ones rejected. Anodes are stamped out of sheet metal, usually nickel. This machine produces complete anodes, accurately stamped, bent to shape and lock-seamed from flat nickel strip. Each single anode is carefully inspected. Now for grids, which are being made in long lengths on this machine. As the machine spins round, it anchors the fine grid wire into notches made automatically in the supporting wires. The lengths are cut into individual grids. The operator controlling the machine can see them enlarged on a ground glass screen. Each grid is stretched to correct size and shape, and its dimensions checked in a gauge. Heaters for indirectly heated cathodes are made from tungsten wire. The wire is bent to an M or V shape. These wires are next clipped into frames, immersed in a bath containing insulating material, which is later baked on by passing a current through the wires. Nickel cathode tubes are cut to length, mounted in frames, and sprayed with barium and strontium carbonates, from which the emissive surface is produced later on. In this case, the heaters are inserted into the coated tube at an early stage. Now you can see that most important component, the getter, being made. It is being electrically welded onto a finished assembly. This machine makes the lead-in wires, which you will recollect are composed of 3 parts. A stout pin for the valve holder, a thinner wire to which one of the valve electrodes is welded, and between them a short length of wire which forms an airtight seal in the glass base. The lead-in wires are loaded into the base-making machine and are automatically fed, 9 at a time, into a jig. A glass ring is placed in position round the wires, and the jig is made to revolve under gas flames. The glass softens, and the machine presses it to form the base. When cold, the bases are inspected. The support wires are then cut to length by one machine, and in the next they are bent to the positions they must assume for the components to be welded to them. Here's a valve assembly section in a thermionic valve factory. There are many different types of valve, and therefore many different forms of electrodes, and many different methods of assembly. These are just a few examples of the operations involved. You have seen many of these operations earlier in this film, performed deliberately and slowly to show you what is done. Now that you see the valves assembled at production speed, you can appreciate that these delicate operations demand great skill and dexterity on the part of the operators. The next step is to seal the assembly into the glass bulb and then pump out the air, so forming a vacuum. Blowpipe flames soften the glass at the junction of the envelope and base, and pressure is applied to form the joint. The valves are transferred to this machine, in which they are pumped continuously to create the vacuum. They pass through a heated tunnel which helps to drive off the gas. Then through coils carrying high-frequency currents which heat the metal parts and drive off more gas. A current through the heater heats the cathode and so reduces the coating on the cathode to oxide, thus forming the emissive surface. High-frequency currents also evaporate the getter to absorb the last traces of gas. After being sealed off, the valves are mounted in racks and are operated for a period under controlled conditions. During this time, further changes occur in the cathode coating, resulting in improved emission. Lastly, the valves are tested for emission, vacuum, insulation, and operating characteristics. In the automatic high-speed tester, the valves are plugged into holders which move to a number of successive stations. At each station a different test is applied, and if a valve fails in any one of these tests, an automatic hand removes it from the machine. In addition to these routine tests, the Quality Control Laboratory continuously tests batches of valves selected at random from the production line. Any falling off in quality is detected at the earliest possible moment, so that steps can be taken to correct it before the trouble can assume serious proportions. That, then, is how the many different parts of a valve are made and put together, and how valves are manufactured under mass production conditions. We hope we've shown you enough to indicate that valve manufacture is a job for a team, that the research worker, designer, plant engineer, laboratory technician, supervisory staff, and the operator all have essential parts to play. So when you next listen to the radio, watch television, or possibly work with equipment employing thermionic valves, perhaps you'll remember something of what goes into the production of these outwardly simple, yet in reality complex, devices.